Here's problem 1510. A horizontal plank, M equal to 2 kilograms, L equal to 1 meter, is pivoted at one end. A spring constant 1,000 newtons per meter, is attached at the other end, as shown in the figure. Find the angular frequency in radians per second for small oscillations. Alright, so we have a spring with spring constant 1,000 newtons per meter. And we're going to have small oscillations, say at some angle theta here, and we're going to subtend through an arc here, arc equal to the radius of the arc times the angle in radians, L times theta. And the spring is going to pull back on the plank at that point, so the force of the spring is going to be equal to a negative k times that arc length s, because it's pulling along the arc. So that's going to be equal to a negative k L theta at that point. And that's going to be a torque. So there's going to be a torque pulling with this force, F like this, with a moment arm equal to L. And hence our torque at that point is going to be equal to force times moment arm L, which would be equal to negative KL theta times L, which would be equal to negative KL squared times theta. That's the torque acting at that point. We also have another force. We have gravity acting at the center of mass, mg, and that would supply a torque as well. The thing is, though, that we've already set this system up before we start the oscillation. And so the gravity torque has already been canceled out by the new equilibrium position. The spring has been pushed down a little bit due to the pull of gravity, and we've established that equilibrium position. So in a sense, gravity has been eliminated from our consideration as far as the oscillations go, because it's already established a new equilibrium position that is taking gravity into account. So our new net torque is only due to the extra pull of the spring. We also know that the net torque, according to Newton's second law for rotations, is equal to the moment of inertia times the angular acceleration. And in this case, that's going to be equal to the moment of inertia of a rod about its end, which is going to be 1/3 ml squared, and then the times the angular acceleration. Alright, so these two torques should be equal, because the net torque is being provided by the spring torque. And so we have that 1/3 ml squared times the angular acceleration equals a negative kl squared times theta. Well, the L squares cancel out, and the angular acceleration is the second derivative of theta. So we have the second derivative of theta with respect to time is equal to, and then dividing by m and multiplying by 3, we'll have a negative 3k divided by m times theta. This is a second order differential equation that we know describes simple harmonic motion, and we can identify the constant in front of the theta as being omega squared. So omega squared is equal to 3k over m, which means that omega is the square root of 3k over m, which is going to be 3 times 1,000 over 2 kilograms square root, and that is equal to 38.73 radians per second. So the angular frequency for small oscillations for this simple harmonic system is 38.73 radians per second.